So, uh, had you ever tried to plan something really complex? I mean, think about a multi-city travel itinerary, tight budget, specific dates, maybe even, I don't know, a weird requirement like no smoking, private rooms only, oh, and pets have to be allowed.
It sounds like a total nightmare, right?
And even with these amazing AI tools we have now,
No.
getting a plan that's actually perfect, like totally solid, it can still feel kind of impossible.
Oh, indeed, yeah. And large language models, LLMs, they're brilliant at understanding natural language, talking to you.
Right.
But they often struggle with let's say, the rigorous logic, the multiple layers of constraints you need for really complex planning.
So they give you something, maybe?
Yeah, they might give you a decent suggestion, something that looks okay, but it's not guaranteed. There's no guarantee it's actually sound or complete.
Okay, and then on the other side, you've got these super powerful algorithmic solvers, like the meticulous accountants of the tech world. Maybe
Yeah.
they can crunch the numbers, guarantee a solution if one exists.
That's the key part, if one exists.
But they speak like formal logic, code,
Hmm.
not plain English, not human requests.
Exactly.
So what does that actually mean for us trying to use this stuff? It feels like we're often stuck, between an AI that's easy to talk to but might mess up the details,
Imprecise.
and one that's super precise but honestly almost impossible for a normal person to use directly.
Right. User unfriendly is putting it mildly sometimes.
So this deep dive, it's all about a pretty fascinating new framework that's really trying to bridge that exact gap. We're looking at sources that propose this system, combining the intuitive power of LLMs, the part that understands us,
Right.
with the rigorous precision of these formal verification tools. Specifically, they use something called an SMT solver.
Satisfiability modulo theory. It's a bit of a mouthful.
Yeah, it is. But think of them as these incredibly precise logic engines. They figure out if a whole bunch of complex conditions can all be met at the same time, and if so, how.
That's a good way to put it.
So our mission today, really, is to give you a shortcut to understanding how we can get these perfectly tailored, complex plans. We'll cover some surprising facts about how it's done and, hopefully keep it interesting along the way. Okay, so here's where the approach gets really, really interesting. Let's break down the strengths and weaknesses of these two different technologies when you try to use them for planning.
Right. So on the one hand, you've got the LLMs. They excel, as we said, at interpreting human input, understanding all the nuances of how we talk, asking questions, engaging dynamically.
Super flexible.
Very flexible. Ask them almost anything, any which way. But, and it's a big but, they can really struggle to rigorously solve complex planning problems, especially when you have lots of intricate constraints all interacting.
Like dominoes if one falls.
Exactly. Their responses might seem good enough, for simple things, but they lack those formal guarantees. They could be subtly flawed, maybe in ways you don't immediately notice.
So like that super chatty friend who seems to know everything, but you maybe wouldn't trust them to balance your checkbook for a really complicated trip down to the last cent.
That's a fair analogy, yeah.
But beyond just the budget, what are some of the other ways LLMs might fall short here? Where does this new framework really offer a breakthrough?
Well, that's a great point. LLMs can sometimes hallucinate, is the term people use?
Right, you make stuff up.
Or just guess, essentially, when faced with complex logical dependencies. And that can lead to plans that look okay on the surface, but are actually fundamentally flawed or, just impossible.
Okay.
In contrast, these algorithm-based solvers, like the ones built on constraint satisfaction problem CSPs or Boolean satisfiability SAT solvers or the SMT solvers we're focusing on, they are built for logic, rigorous logic.
Sounded complete, you mentioned.
Exactly, sounding complete, which means if a solution does exist for your complex multi-constraint problem, they will find it, guaranteed. And maybe just as importantly, if a solution doesn't exist, they won't just fail silently or give you nonsense. They'll tell you definitively, nope, this combination is impossible, and here's why.
But the catch is?
The catch, as you said, is they have a steep learning curve. They don't understand, hey, plan me a trip. They need things formalized. They can't process ambiguous natural language.
Ah, the quiet, meticulous problem solvers. Brilliant, but yeah, you can't just casually ask them to figure out my taxes. You have to feed them every single number, every rule in their very specific language.
Precisely.
So this framework we're looking at, it's really asking, can we get the best of both? Can we combine them for something that's both rigorous and user-friendly? All right, let's dive into the specifics then. The core idea sounds really clever. Instead of the LLM trying to solve the problem itself, it acts more like a translator, a facilitator. How's that work?
Yeah, translator is a good word for it. What's really fascinating is how the framework uses the LLM's strength understanding language to generate code.
Oh.
So, you give it your query in plain English. The LLM first translates that into a sequence of natural language instruction steps. Like, it breaks down the problem formulation into English steps first.
Like a recipe written out.
Kind of, yeah. And then it translates those steps into actual executable code, a code that's specifically designed to talk to an SMT solver like the popular Z3 solver.
Okay, so walk me through an example. Let's use that trip again. Plan a trip from St. Petersburg to Rockford, 3 days, March 16th to 18th, 2022. One person, budget $1,700. What happens?
Right. So the LLM might first generate internal natural language steps like, okay, step 1, define variables for the travel dates for the transportation legs between cities. Step 2, assert that the first transportation must happen on the first day, day 0. Step 3, assert the last transportation happens on the last day, day 2 in this case. Then it takes those steps and translates them into the actual formal code the SMT solver needs. Something like, defining specific variables and adding constraints like s.add departure date equals 0 and s.add return date equals 2. It rigorously encodes all those constraints, dates, budget, locations, into the solver's language.
And what's really striking, the sources say it learns this pretty fast. Like with only 3 examples in the prompt, it can figure out this whole translation pattern and apply it to new requests.
It is remarkable, yeah. Just 3 examples.
That seems pretty impressive for such a complex task, translating intent into formal logic and code.
It really is. It speaks volumes about the LLM's ability to pick up on underlying patterns, not just in language, but in the structure of logical problems, even with minimal specific training for this particular task.
So this deep dive isn't just about, hey, we connected 2 things. It's about the real benefits, the actual breakthroughs this approach delivers. They've identified several key features, right?
Absolutely. And if we look at the results, they're quite compelling. The first big one, the major insight really, is the superior planning success rate. Just a huge leap in reliability.
How much better are we talking?
Well, they tested it across different big LLMs, GPT-4, Claude 3 Opus, Mistral Large, and on their travel planning tests, it achieved final pass rates, meaning successful plans, as high as 93.3% and 93.9%.
Wow, okay, over 90%.
Yeah. Now, compare that to other methods of using LLMs with tools, like a framework called LLM Modulo. On the same tasks, it only got pass rates of 20% and 65%.
Wait, 20%? So you're saying this hybrid approach takes something that failed like 80% of the time in one setup and makes it succeed over 90% of the time?
Exactly. It's not just a little improvement, it's a massive jump. It's fundamentally changing the reliability of AI for this kind of planning.
That really is a game changer.
No.
Okay, what else?
The second crucial insight, and this is really neat, is how it handles failure. It's the feedback interaction on unsolvable cases.
Right, because sometimes the request is just impossible.
Precisely. Most AI systems, if you ask for something impossible, they just stop or give you garbage.
Yeah, they just fail.
But this framework, if your query can't be solved, like your example of wanting 5-star hotels on a tiny budget, the SMT solver doesn't just fail. It identifies the exact constraints that conflict. It says, this budget constraint clashes with this hotel quality constraint.
It pinpoints the problem.
Exactly. And then the LLM takes that specific feedback, analyzes why it failed, maybe uses tools to gather more info, like checking real hotel prices, and then proposes concrete, helpful suggestions to modify your query.
Like, hey, that 5-star hotel for $50 a night, that's not going to work.
Yeah.
How about we increase the budget or maybe look at 4-star places instead? That kind of thing.
Precisely that kind of thing. And it can get quite nuanced. It could suggest changing dates slightly if flights are the issue, or maybe a different nearby city. It uses its reasoning.
So it becomes collaborative. It helps you fix the request.
Yes. It turns it into a dialogue. This interactive repair mechanism, they found, transforms somewhere between 81.6% and 91.7% of initially unsolvable problems into solvable ones.
Wow.
And it learns quickly. The success rate jumps up fast within the first, say, 5 back-and-forth interactions. Yeah. It really turns that dead end into, okay, let's figure this out together.
That's incredibly useful. But, I mean, with something this capable, are there known limitations? Like specific types of problems or edge cases where it still struggles a bit or maybe isn't quite as optimal?
Well, that actually leads nicely into the next point, which is its remarkable strong zero-shot generalizability.
Zero shot meaning It wasn't trained specifically on those new things.
Exactly. It means it could tackle entirely new types of planning problems it had never seen examples of during its minimal setup, and still perform exceptionally well.
Okay, so it's not just a one-trick pony for travel.
Not at all. While the main examples were travel planning, they tested it on totally different combinatorial planning tasks.
Like, give us some examples. What kind of weird stuff did they throw at it?
Okay, so things like block picking. Imagine selecting unique blocks with different colors and points to maximize your score under certain rules.
Right.
Or task allocation, assigning different tasks to various robots. Maybe some robots are faster or better suited than others, and you want to minimize the total time to finish all tasks.
Okay, complex scheduling.
Yeah, and the classic traveling salesman problem: find the shortest route to visit a set of cities exactly once and return home.
Uh-huh.
And even warehouse problems, maybe optimizing storage or retrieval paths. On these completely new domains, problems it hadn't seen before, it achieved an average of 89.0% optimal rates. Zero shot.
89%
Yeah.
optimal on problems it never saw before.
Correct.
Wow. Okay, so it's not just a travel planner. It's more like a general purpose super planner. That's incredibly adaptable.
It appears to be, yes,
Yes,
highly adaptable. And they also mention its high prompt robustness, meaning it wasn't too fussy about how you asked the question. It could handle a pretty wide range of ways of phrasing the request, different prompt formulations, and still work effectively. It wasn't overly brittle or dependent on getting the prompt exactly right.
It's huge for practical usability, right? You don't need to be a prompt engineer to use it.
Exactly. It makes it much more accessible.
Okay, you've given us a fantastic overview of what it does, and the results sound amazing. But how does it actually pull it off? What's happening like under the hood during this complex dance between the LLM and the solver?
Right. Let's peel back the layers a bit. It happens in a few key stages. First up is problem formulation.
Okay.
This is where your natural language requests, like, I want to travel from city O, visit K other cities, return to O, and do it all in days, gets translated into a more formal structure the system can begin to work with.
So step one is just understanding the basic pieces of the request, getting rid of the ambiguity. What's next?
Precisely. Then comes query step generation. This is where the LLM, as we touched on, transforms that initial request into a series of executable steps, but still expressed in natural language.
The recipe analogy again?
Exactly, like a detailed instruction manual for how one would set up this problem logically. For that query, travel 2 destination cities in 5 days, the LLM might generate internal steps like 1. Set up variables for the dates of the 3 transportation legs needed. 2. Add a rule. The first leg must be on day 0. 3. Add another rule. The last leg must be on day 4. 4. Add a rule. The middle leg can be on day 1, 2, or 3.
Okay, breaking it down logically in English first.
Yes. And this part is taught, remember, using just those few human-crafted examples, often broken down by constraint type, like here's how you handle destinations, here's how you handle dates, here's how you handle transport.
That's fascinating. It's like teaching it the process of setting up the problem. Then what? Does it translate that recipe?
That's the next layer, step code translation. The LLM takes those natural language steps it just generated and translates them into the actual Python code, or similar, that the SMT solver understands. This code defines the variables formally, asserts the constraints using the specific syntax of the solver, like Z3.
So it's writing the program for the solver.
It is literally writing the program. An example might be taking that step about travel dates and generating the precise code like s.add and tdate 0 equals 0, tdates 2 equals 4, making sure the solver knows the exact start and end days formally.
And then finally, the SMT solver gets to do its thing.
Finally, yes, the SMT solver stage. The code the LLM generated is executed. This formally lays out the entire problem for the solver, and because SMT solvers are sound and complete,
It finds the solution if one exists.
it finds a guaranteed valid solution if one exists, giving you a formally verified plan. Or if the constraints clash, it doesn't just crash, it outputs specific, unsatisfiable reasons. It can pinpoint the exact conflicting constraints, maybe using a function like Z3's get and satcore, saying, for instance, constraint budget $1,700 conflicts with constraint hotel costs $300 night based on available data for destination X.
And this is what's so cool. The LLM doesn't just report that error back to you, right?
Right.
It uses that specific reason.
Exactly. It doesn't just throw up its virtual hands. It uses those precise reasons from the solver to understand why the plan failed.
And then tries to fix it.
Yes. That kicks off the interactive repair loop we talked about. It uses its reasoning, maybe its common sense knowledge, perhaps calls out to external tools or APIs, like a flight check API, to see if a specific flight actually exists on that day.
Okay.
And then it suggests concrete modifications. If that flight from St. Petersburg to Rockford doesn't exist, it might analyze the situation, say, okay, that connection isn't possible, suggest changing the destination, maybe run a flight search API to find alternative destinations that do have flights from St. Petersburg within the time frame, and present those options back to you.
So it actively tries to find a workaround based on the specific failure point.
Exactly. And then you, the user, can give feedback, okay, try that alternative city, or no, I really need to go to Rockford, let's change the dates instead. And the process iterates, reformulate, translate, solve, maybe get feedback, suggest modifications, until either a valid plan is found or you agree it's just not feasible.
That's a powerful loop.
Yeah.
And you mentioned the efficiency. It's not just effective, it sounds reasonably quick and, dare I say, cheap.
Relatively speaking, yes. For plans that were solvable right away, the average cost they reported was around 74 cents per query. Took about 4 minutes on average. And interestingly, most of that time wasn't the solver, it was the LLM translating the steps into code.
Ah, the translation is the bottleneck.
It seems to be a significant part, yeah. And for the interactive repair, when it had to go back and forth, it was even cheaper per cycle, about 65 per iteration, and faster too, around 34 seconds per iteration to analyze the failure and suggest a fix.
So pretty efficient for solving potentially very tricky problems.
Yeah, definitely practical.
Okay, so stepping back, what does all this mean for you, our listener? As someone interested in this space, why should you care about this blend, this hybrid of LLMs and formal solvers?
Well, it really raises an important question, doesn't it, about how we interact with AI for complex, high-stakes tasks. This framework points towards a future where we can get truly reliable, tailored solutions for problems with many constraints.
Things beyond travel planning, presumably.
Oh, absolutely. Imagine needing to schedule a really complex project at work with dependencies and resource limits, or managing the logistics for a big event, or even just, planning that perfect family vacation that actually accommodates everyone's needs, preferences, and the budget.
So instead of banging your head against the wall, trying endless variations, or just getting swamped by information,
Right.
you could potentially get a plan that's not just thrown together, but is guaranteed to be logically sound, internally consistent.
Exactly. It's about getting that knowledge, that solution, quickly but also thoroughly. It could lead to those real aha moments where a problem that seemed impossibly complex suddenly becomes manageable, solvable.
It really feels like it respects your time, doesn't it? Either finds the solution efficiently or helps you figure out why it's not working and guides you to a fix.
It absolutely does. It aims to give you the best of both worlds.
Yeah?
That easy natural language interaction we like from LLMs,
Uh-huh.
combined with the hardcore logical rigor you need for serious real-world planning where mistakes can be costly or frustrating. It's about empowering you, really, to tackle problems you might have just given up on before. Saves a lot of mental energy.
So as we wrap up this deep dive, it definitely feels like we're seeing a really exciting step forward in how AI can handle complex challenges.
Yeah.
This idea, this blend of human-like understanding from LLMs and the formal, verifiable logic of solvers.
Yeah.
It seems incredibly powerful.
It really does present a compelling vision, I think, for future AI applications, moving beyond just fetching information or simple tasks towards robust, verifiable, complex planning and problem solving.
Are there caveats, downsides?
Well, one important thing the sources do highlight is that the framework as it stands relies heavily on the data it has access to, like in its database for flights or hotels. It doesn't currently have an inherent capability to distinguish if that underlying information is itself unsafe or incorrect.
So garbage in, potentially garbage out, still applies. If the flight data is wrong, the plan might be technically valid according to the solver, but still useless in reality.
Precisely. The quality and safety of the output plan is still fundamentally tied to the quality and safety of the input data and the information it can access. That's a critical piece to remember.
Okay, that makes sense. So for you, our curious listener, maybe something to think about is this. How might this kind of hybrid approach change the way you tackle complex decisions, either in your work or your personal life? What other kinds of problems, things that seem maybe unsolvable right now, might actually become tractable when you can combine that human-like intuition and ease of use with true machine-like precision and verification.
It opens up possibilities.
It really does. Well, thank you for joining us on this deep dive into this fascinating intersection of large language models and formal verification for complex planning. We really hope it sparks some new ideas for you.